Now let's learn about the depth first search. So last Monday we already learned about graph and how to create a graph with Python. And now let's look at the concept about DFS, depth first search, and what is the DFS algorithm, and some properties of DFS. So what is depth first search? We want to check subgraph. Subgraph S of a graph G is a graph such that the vertices of S are a subset of the vertices of G. So can you understand? The vertices of S, so I have S, are a subset of the vertices of G. So I have G. So this is S, this is G. So S is a graph, and G is also a graph. Then, if you know, a graph means it is a collection of vertices and edges. And then we have another graph, G, and we have another vertices and edges. Subset. Subset means it is the element or some of this V belongs to this V. So let's say this one. Let's say I have this one is A, B, C, D, E. Okay. Then in the graph G, we have the V, which is A, B, C, D, E. And then we have another, we have these edges, but I do not explain the edges. And then S, what about S? S, we have only B, 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 and C. So we call this is the subset. So we call this is the subset of the vertices of G. So B, B and D and C is the subset of A, B, C, D, and and the edges of S are a subset of the edges of G. So the same. Yeah, we have, let's say this is the edges of S, then these edges should be the subset of G. We will have a spanning graph of G is a subgraph that contains all the vertices of G. Contain all of the vertices of G. We call it, this is the spanning subgraph. The spanning subgraph, if you look at this one, this is the graph. Let's suppose we have A, B, C, D, E. So the spanning subgraph means the vertices should be the same. This one, okay, we have A, B, C, D, E. But the only difference is the edges. So we can remove the edges. And if this one is the edges of the spanning subgraph, then we can say this is the spanning subgraph because all the vertices are the same with G except the edges. Okay. We will see more examples. We can also look at the connectivity. A graph is connected if there is a path between every pair of vertices. So we call this is a connected graph because there is a path. What is path? We call this is a path because there is a way from one node to another node. There is a way from one node to another node. There is a way from one node to another node. Okay. So this is connected. But there might be a case where the graph is not connected. So a connected component of a graph G is a maximal connected subgraph of G. So if you look at this way, this is non-connected graph with two connected components. So this is the first connected component. This is the second connected component. So we call this is a non-connected graph with two connected components. So we want to see the maximal connected subgraph. Then if you look at this one, so how many connected components do we have? We say we have one connected component. We have another one connected component. So we have two connected components. So we have another definition about trees and forests. Tree. Sometimes we call it forestry. Okay, so that's why we call it tree. Okay. But many people just make the definition about tree. This is tree in a graph. Please be careful. We have the tree that is related to graph, and we have another tree. So if you still remember the tree that we learned in the section in before the mid exam, it is the tree with root. So let's say this one is a binary tree. But the tree in the graph is, yeah, you can see this one. A tree is an undirected graph. Okay, do you still remember undirected graph? There is no direction, such that T is connected and T has no cycle. So this is a tree. This node or this vertex is connected to this node. It is connected to this node. It is connected to this node. It is connected to this node. And there is no cycle. Cycle means this one. Yeah, we have no cycle. This definition is different from the one of the rooted tree. I mentioned to you rooted tree. So we have this is the tree, and we have the root, and then we have the leaf. Okay, so here the last section. Okay, here is the leaf, and the upper side is the root. And we can also say this is the children. So this is the children of this parent. And this is the grandchildren from this one. A forest is an undirected graph without cycles. So this is a forest. So we have a graph. We have graph And we have also another graph with a single node and a collection of this tree. We call it a forest. So the connected components of a forest are trees. The connected component. So if it is connected, okay, then we call this is a tree. Or yeah, this is a tree. This is another tree, and so on. Yes, because this is the connected components. There are another kind of definition, we call it spanning trees. And also we have spanning forests. A spanning tree of a connected graph is a spanning subgraph that is a tree. So what is spanning subgraph? Spanning subgraph. It is a graph with a subgraph with all vertices of G. Okay, a subgraph S with all vertices of G. So go to definition, we can check. So a spanning subgraph of G is a subgraph that contains all the vertices of G. And we have a spanning tree. A spanning tree is a spanning subgraph that is a tree. So what is a tree? The definition of a tree is everything should be connected and no side. So by the definition, a tree is T is connected and T has no side. So this is tree. So a spanning tree is not unique unless the graph is a tree. It means you can have a lot of spanning tree from a graph. Okay, a spanning tree is not unique unless the graph is a tree. So this graph, yeah, this is a graph. Okay. And if you want to create a tree, we can have this one is a spanning tree from this graph. This is also a spanning tree from this graph. This is also a spanning tree from this graph. So there might be more than one spanning tree. So spanning trees have application to the design of communication networks. And we have also a spanning forest. Spanning forest graph is a spanning subgraph that is a forest. Okay, so the definition of this one is similar with this one. Now, let's look at an example how we can leverage the spanning trees with the Kruskal algorithms example. If some of you in your team project, you try to apply the Kruskal algorithm. So let me show you how the Kruskal algorithm works. Let's say we have this graph. So A is connected to B and there is cost 2. B is connected to D, there is cost 1. B is connected to E, there is a cost 7, and so on. Okay. At first, we need to sort all the edges in a non-decreasing order of the width. What does it mean, non-decreasing? Non-decreasing means increasing. Okay. So if it is increasing, then we will check from the smallest, from 1, and then 2, and then 3, and then 4, and then 6, and then 7. The second step is pick the smallest edge. So it means we need to select one. Check if it forms a cycle with the spanning tree formed so far. If the cycle is not formed, then include this edge. Else, discard it. So because we want to make sure that a tree is connected, a tree is connected, and a tree has no cycle. So we want to make sure these two definition. So we will do the repetition until there are v minus 1 edges in the spanning tree. So let's see. At first, I will select one, B and D. Okay, we'll check. Is there any cycle of this one? Of course, no. Then we can go to the next. The second is we will check number 2. So it is connected P and D and P and D. Next iteration is 3 because we need to use the non-increasing order. And then next we have D and E. So the spanning tree will be this one. So this will be the spanning tree. A, B, C, D, and E. And the distance is 2, it is 1, it is 3, and this is 4. So this is the Kruskal algorithm. And this is also a kind of finding the shortest path. Now, we would like to learn about the depth first. DFS, it is a general technique for traversing a graph. So using the crystal, it is very simple. We just solve the distance and then do the traversal. So in the DFS, we will traversal of a graph by visiting all the vertices and edges and determine whether G is connected. And then computes the connected components of G and computes a spanning forest of G. Okay, so the steps, first we will visit and then check whether it is connected and then compute the connected components and then compute the spanning forest. So here as on a graph with n vertices and m edges. So it mentioned that it will take O n plus m. N means the number of vertices and m means the number of edges. It is only the addition, okay? N plus m. DFS can be further extended to solve other graph problems. For example, find and report a path between two given vertices. Or we want to find a cycle in the graph. So the depth first is to graph what Euler tour is to the binary trees. We can use the DFS for the Euler tour. So this is the algorithm. We have two functions. The first is DFS G, and the other is DFS G, B. The algorithm uses a mechanism for setting and getting the labels of vertices and edges. The input will be a graph, and then the output will be labeling. So we need to label the edges as discovery edges and back edges. So we have U for all G vertices, and we want to set all the U as unexplored. We want to set E as the edges, and we want to set all E as unexplored. And we want to check for all V in the vertices. If the label is unexplored, do this algorithm. If the the V is unexplored, then let's do this algorithm. Now, what is inside this algorithm? The input is a graph and a stub protects V with G. So we want to get the label of edges G in the connected component of V as discovery edges and back edges. So we will check what is discovery edges and what is back edges. At first, we will set the label as preceded, and then we will do the loop like this one. If you still remember, we have the incident edges. What is incident edges? If we have a V, so the incident edges is the edge that is incoming or outgoing from V. So we want to check for all incident edges of V. So we want to check this. We want to check this one. And if the label is unexplored, check the opposite of V. So check the opposite of V. The opposite of V, let's say this is U. So check the opposite of V. Okay, let's say this is W. Because we set this W. And then let's check the opposite of V with the edge E. So this is the edge E. If the label of W is unexplored, okay, so if this one is unexplored, then set the label E as discovery. So this is now we say that, okay, we want to use this X to go from V to W. And then we will do again the DFS. So we will do the recursion. If the label is already explored, I'm sorry, if the label is already explored from here, then set the label E as spec. What is spec? So we have discovery as discovery edges, and we have back as back edges. Okay, we have discovery as discovery edges and back as the back edges. Now let's see the example. This is the Python implementation. If we use the DFS G, U discover, so we will check what is the incident edges U, and then V will be the opposite view from the respective of X. If V not in discover, so if V not in discover, then discover V equals to V. So DFS will be started again. So we will check another V whether it is already discovered or not. Now let's see how the algorithm works step by step. So we have the symbol like this one. A is unexplored with the blue color. The yellow color means the vertex has been visited. If it is with the line, it is unexplored X or UE. If it is lined with an arrow with a solid line, then it is a discovery X. And if it is with the dotted line like this is the back X. Now, let's assume it starts from A. Okay, I start from A. And for all the states, it will be UV, 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 UV. UV means unexplored products. What about the X? The X AB, it is unexplored X. The XBC, it is also unexplored. Unexplored. So all of them are unexplored. Okay, we have AB, BC, CA, CD, DA, CE, and E. Next, because I start from A, now when you look at the algorithm, set the label V as visited. So set the label A as visited. Oh, this one should be visited. And then check what are the incident edges of V. Let me change this one. This one will become visited. It will become visited. And then we want to check what are the incident edges of V. So the incident edge here we have A. So this is the incident edge. Check the label. Is it unexplored? Okay, at the first state, it is unexplored. Because unexplored, so we want to check what is the opposite of E. So what is the opposite? The opposite is B. Then check the label B. Check the label B. Is it unexplored? Because it is still unexplored. So set the label E as discovery. So set the label A and B as discovery. Discovery as D. And then do this one. DFS G, W. So we start from okay, so we start from B. Now we go back again here, B. So set the label V as visited. So set the label B as visited. Now check all the E from V. So check all the X from B. So we have this one. And then check if the label E is unexplored. So BC. BC is originally it is unexplored. Unexplored means unexplored at UE. And then we want to check the opposite of B. The opposite of B is C. So check the label of C, whether it is unexplored. C is still unexplored. Then make the label as discovery. Now we change this one into discovery. We change to D. And then again we do the recursion to DFS. Now we are now in the C. So after we are in the C, again set the label C as visited. Okay, set the label C as visited. Now check the incident edges. So we have the incident edge here. Get the label unexplored. Okay, this is unexplored. C to A is unexplored. Now check the opposite of C. The opposite of C is A. Now get the label of A. If the label is unexplored, what is the label of A? The label of A is already visited. Because it is already visited, so we will not go here. We will go here. Set the label of E as back edges. So C to A, now it becomes back edges. After we have this stack edges, now we will go again to the other possible edge. The other possible edge is this one. Sorry, the animation here. So this is the other possible edge. Then we will check E is unexplored, C to D is unexplored. Yeah, originally it is unexplored. And then we want to check what is the opposite of C. The opposite of C is D. So D is unexplored. Yes, it is not visited. Then set the label E as discovery. So set the label E, which is C to D, as discovery. We have DE. And then we will do again DFS G, W. So D has been visited. Now we will check from D. From D, we need to check another possible. So D is visited. Now we want to check what are the incident edges. So this is the incident edge. Is it unexplored? D to A, it is, yeah, originally it is unexplored. Then we check what is the opposite of D. The opposite of D is A. Check the label of A, whether it is unexplored. Now we know that A has been visited. Then we will not do this one. We will go here. Set the label as back edges. So the DA, D go back to A will be back edges. As you know, it is a kind of recursion. So is there any incident X from D? There is no other incident X because there is no other incident X from D. So we will go back to the previous state. So the previous state is now in the C. In C, we still have one more X. We still have one more X, and then we check. Is the E is unexplored? CE is unexplored. Yeah, originally it is unexplored. Yes. So let's check what is the opposite of C. The opposite of C is E. Now check. Is E is unexplored? Yes, this is unexplored. Then set the label E as discovery. So CE is discover X. And then go back to this function. Now, at this set in E, we will do the visited. Okay. So set the label V as visited. And then check all the possible ads. This is the ads. And then we check whether the label E is unexplored. EA, it is unexplored, yes. And then check what is the opposite of E. The opposite of E is A. And then check the label of A. The label of A is visited. Then we go to here. So set the label EA as back edges. So at the end, we will have this result for the DFS. So DFS is good for some application. For example, the maze tool. The DFS algorithm is similar to a classic strategy for exploring maze. So we mark its intersection, corner, and dead end as vertex visited. So this is vertex, 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 vertex. And we mark its corridor or edge traverse. So this is the edge, this is edge, this is edge, this is edge. And we keep track of the path back to the entrance. So for example, this is the starting vertex by means of a rope or recursion step. So if you start from here, okay, if we can go here, okay, then go next. We can go here and then check next. and check next. If it is a loop or a cycle, then go back, go back. So we go to the next. And if this is dead end, go back. If this is dead end, go back. And then go here, and then go forward, and so on. So the properties of DFS, we have two properties. The first property is DFS visit all the vertices and edges in the connected component of V. So it will visit all V. So we need to visit all V. And the discovery edges labeled by DFS G, V form a spanning tree. This is the spanning tree of a connected component of V. In DFS, setting or getting the vertex and the label for the edge will take O1 because we just want to check if the label, if the vertex is labeled unexplored, that is one time. If the edge label is unexplored, it is also one time. Its vertex is labeled twice. So the first is unexplored and the other is visited. Its label is labeled twice, unexplored and discovery or backends. So the method incident edges is called once for its vertex. So using this kind of analysis, we can say that the DFS runs in ON plus M. This time provided by the graph is represented by adjacency disk. Do you remember adjacency disk? Okay, we learned about this on Monday, so please check that one. And we have this property. The summation of the degree V equals to 2 multiplied by M. So there might be another kind of algorithm for the DFS, for example, path finding. So I want to find the path from an origin V to Z, a destination. So we can specialize the DFS algorithm to find the path between two given vertices U and Z using the template method pattern. So if you look at this one, okay, so the structure is the same with the one that we learned before. The structure of this DFS is the same, but the only difference is we try to apply stack. So we use push and we use pop. So push is in the beginning and pop is at the end. And the remaining will be the same with the DFS. If the V equal to Z, so it means if the origin already reached the destination, then return the output. If it is not, then we will do the loop. So we use a stack to keep track of the path between start vertex and the current vertex. As soon as destination vertex is encountered, we return the path as the contents of the stack. And we can use also the DFS for cycle finding. So the cycle finding means we will find the simple cycle. You should remember. Okay, we have simple path and we have simple cycle. So the DFS can be used for finding the simple cycle. Again, this is the shape. The sum part, like this one, finding the unexplored and find the opposite is the same. This is also the same, but the only difference now we use stack in between. We use stack in between. And if the empty stack is available, so we also use this empty stack to refer for the backends. So that's the only additional for finding the symbol title using DFS. Okay, so let's have a break. I will continue after the break.